Okay, trig substitutions. However, today's a little bit different. You might remember this is one of the examples we did in great detail, step by step. I want to just focus on the original question and then the answer. All right, so there was the question, the integral, and then after all that work, there's the answer. And here's the example we did. And again, there's the answer. After all that grueling work, that's the answer we came up with. And you might notice a few things, right? A lot of things are identical. When we have the minus x squared inside the square root symbol, look at how many things are identical. You can probably also notice that that 9 from the question shows up in parts of the answer. And you can probably make a pretty logical guess where that 3 is coming from. That's the square root of 9. On the other question, notice where that 25 keeps showing up. And sure enough, 5 is the square root of 25. So if I asked you to come up with the answer for this question, but I did not insist that you show step-by-step work, you would already know a huge chunk of the answer. And you say, well, gee, that 49 will probably go right there. And that 49 will probably go right there. And since 49 is 7 times 7, I bet there's a 7 right there. And indeed, that would be the correct answer. Now, the neat thing about this, if you remember, we found the area of a circle. And when we did the area of a circle, when we substituted in terms of theta instead of in terms of x, we had to adjust the limits of integration, right? Because negative 10 to 10 was when we're in terms of x, but when we had adjusted to theta, we had to adjust it from negative pi over 2 to positive pi over 2. Now, if we already know what the answer should be if we follow it through in terms of x, we don't have to change the limits of integration. Let's get a little bit of space up here. Okay. First of all, notice what I did with that 2. We've done many integrations where I keep saying, hey, that coefficient will just sit there because that's what coefficients do. Well, since that coefficient is just going to sit there and do absolutely nothing, I can actually put it out in front of the integral symbol. Right? I'll say, hey, I know that 2 is going to sit there. I know I'm just going to multiply everything by 2 when I'm all done. And I can actually just move that 2 out in front. Now, we know what the answer is supposed to end up looking like. Right? We'll have the 100 over 2. Right? The 2 is always there, and the 100 is coming from that 10 squared. Then we'll also have arc sign. And then it's always x over a number. And what is it? Well, we've been taking the square root of the number that's inside. But notice when it's written this way, instead of taking the square root of 100, we're just like, oh, gee, if I saw 10 squared, I know it's a 10. Then, of course, we've got the plus sign. And then we got another fraction. There's always an x in front of the square root symbol. There's always a 2 in the denominator. And that 100 minus x squared reappears there. And then we have to evaluate it from negative 10 to 10. Right? Don't have to change it to theta. Don't have to change the limits of integration. Just have to plug in the number 10 every place I see an x. Figure out that answer. Plug in a negative 10 everywhere I see an x. Figure out that answer. Take the answer from 10, subtract the answer from negative 10, and then when I'm all done, oh, there's that silly coefficient of 2, so I can just multiply by 2. Of course, I can simplify things. And then arc sine of 1 is just going to be pi over 2. Arc sine of negative 1 will be negative pi over 2. And of course, when I have my 5 times 0, that's just going to disappear. So as I continue to simplify, it looks like I've got 25 pi plus 25 pi. That adds up to 50 pi. Oh, but there's that 2, that coefficient. And sure enough, I end up with 100 pi square units without having to do the trig substitution because I knew what the answer should look like. And then just as an aside, you might remember this, the area of a circle with radius r is just pi times radius squared. And I'm sure you figured that out long ago when we first started finding the area of the circle. We'd be like, why are we doing this with calculus? Okay, so again, those are the examples, and there's the general form, right? Anytime we've got that square root symbol and the x squared is being subtracted, right? There were 3 different types of triangles we drew. One of them was this type. And this was the type of integration we could actually do. Well, instead of performing all the step-by-step work, I could just say, hey, if I have the integral in front of me, I know what the answer is going to be. Right? I've got some fractions where the denominators are always 2. I've got an arc sine in there. The square root's always going to be there. X's are going to be there. The only thing I got to be careful about is, well, where am I going to put that a squared and where am I going to put that a? But that's the general format. And on the next lesson, we're going to talk about, well, where do you look to find things like this? But for right now, that's the one you'll need for today. We're going to have a worksheet apparently, and the worksheet, if I remember correctly, just has 2 questions. On one of them, it's just going to be the integral, like, hey, can you just write the answer? If I give you the integral, can you just write the answer? And then on the other one, there'll be limits of integration, so instead of just rewriting it, you then will have to plug in values and come up with an answer. But hopefully this goes pretty smoothly. Awkward spacing for spring break. I would love to have had one more lesson before spring break, but this is a B week, which means calculus would not meet on Friday. And then my understanding is that we're going to take a serious look at lightning student loads for work on Friday. So even if this were an A week, apparently we would probably not have a calculus class. So this is going to be our send-off for spring break. Awkward place to take a break, but it is what it is. And then when we get back from spring break, we'll say, hey, we know how to do this type of trig substitution just by plugging numbers into a formula. What's the formula for the other two, right? And we won't be doing quite as so much step-by-step work. If we just want to integrate, we'll know what a formula to use. But then if we want to plug in numbers and evaluate, then it still gets a little bit slower. But anyway, 2 questions. My hunch is, as usual, you'll be pretty successful. And as always, if you've got questions, shoot me an email. And if we cannot answer questions quickly in email, let's do some Zoom time together.